Hello everyone. In today's lesson, we're going to talk about rates. In physics, we define a rate as how much something changes in a given amount of time. So common rates that you would be familiar with include velocity and speed, as well as acceleration. And these are the three rates that we're going to be considering today. So let's go ahead and get started with speed. Speed is defined as the rate at which distance is covered. So when we look at a speed ratio, we're looking at a ratio of length over time. So the dimension or dimensions of speed are a unit of measurement of length over a unit of measurement of time. So this could be something like miles per hour, or meters per second, or kilometers per hour. As long as we have a unit of distance divided by a unit of time, we have dimensions of speed. Now, when we measure speed, there are a couple of different ways that we can describe what we're measuring. In particular, we can describe instantaneous speed, or we can describe average speed. So let's take a look at the difference between the two. Now, the word instantaneous suggests instant. So we talk about instantaneous speed, we're looking at speed for an object at a particular time. So this is sort of a snapshot. At some instant in time, how fast are you traveling? And you're probably familiar with instantaneous speed from looking at the speedometer in your car. You look at the speedometer in the dash, it tells you you're traveling 50 miles per hour, but you look back an instant later and now you're only traveling 40 miles per hour. So that speedometer gives you an indication of your instantaneous speed. The other consideration when describing speed would be to look at an average speed. And as the name suggests here, we're looking at your average speed over a given time period. So mathematically, this would be your total distance covered in a given time interval. So when we do calculations with speed, we are usually calculating average speed. We'll have measured the distance traveled and calculated, measured the time interval in which we cover that amount of distance, and then we can plug those values into the rate ratio for speed. So in form of an equation, this would be v, we use a lowercase v for the variable that represents speed, equals change in distance. We use the triangle symbol, delta, Greek letter delta for change, over change in time. And this is again going to be an average speed calculation, so we might note v average, but we usually leave that out. Anytime you see this equation delta d over delta t, we're calculating average speed. In order to find instantaneous speed, we would have to examine a graph of position versus time. We'd have to consider a graph of motion in order to find instantaneous speed. And that's something we'll talk about at a later time. So let's take a look at a simple average speed calculation using the delta d over delta t formula. So let's say that we are traveling a distance of 300 miles, and we travel this distance in a total time interval of 5 hours. So, using the equation, speed equals change in distance over change in time, we plug in 300 miles for our change in distance. That's how much distance we've covered. We plug in 5 hours for our change in time. That's how long it took us to cover 300 miles. And we divide through and get 60 miles per hour. So that's a very simple average speed calculation. Now, this is average speed, so that means that during our 300-mile trip, we averaged out to 60 miles per hour. We wouldn't have been traveling at 60 miles per hour the entire time. We would have started at 0. We would need to accelerate to increase our speed. And then to average out to 60, we would have had to have been traveling at some speeds higher than 60 miles per hour along the way as well. Otherwise, we wouldn't have been able to attain that average. So we would have to have both higher and lower instantaneous speed values along this 300-mile trip in order to attain an average of 60 miles per hour. So the average speed gives us a general indication of our rate of distance covered, but it doesn't give us specific information about how fast we were going at any instant in time. So the next rate that we want to cover is velocity. Velocity is just speed in a given direction, which means that velocity is a vector quantity. It requires both magnitude and direction for a complete description. Now contrast that with speed, which is a scalar quantity. It only requires magnitude. So here we have magnitude plus direction with velocity, making it a vector quantity. So when we did our calculation previously and found that our average speed was 60 miles per hour, that's only a magnitude. To make that into a description of velocity, we have to specify the direction of travel. So if we had 60 miles per hour east, we are now indicating the direction of travel as well as the magnitude of our speed. And that makes this a velocity quantity. This makes it a vector quantity, that is, which is describing velocity in this particular case. Now, the important consequence of velocity being a vector is that in order to have constant velocity, we must have both unchanging speed and direction. So what this means is it is possible for you to be traveling at a constant speed, but not constant velocity. For instance, if you're traveling in an arc or curved pathway, we could be traveling at a constant speed of 60 miles per hour along that curved pathway, but because we're changing our direction, our velocity would not be constant. We have to have both constant speed and direction in order for our velocity to be considered constant. So we would have to be traveling in a straight line path at constant speed. Which leads us to our final rate of discussion for today, and that is acceleration. Now, when we go along that curved path and change our direction, we are changing our velocity. And acceleration is defined as the rate of change of velocity with respect to time. So if you're going to write that in equation form, we would say A equals change in velocity delta V over change in time delta T. And so we see the dimensions then of acceleration are speed per time, or to be a little more specific, length over time squared. So we have 1 unit of length in the numerator and then 2 units of time in the denominator. So this could be something like meters per second squared, which is what we'll work with most commonly in physics, but it could also be something like kilometers per hour times seconds. That's a unit of length and then 2 units of time in the denominator. That would also be an acceptable unit of measurement for acceleration. Now, it's important to note that acceleration is going to apply to both increases and decreases in speed, as well as changes in direction. And as a consequence, we find that acceleration, like velocity, is a vector quantity. It has both magnitude and direction. So when we talk about acceleration, we have to give both a magnitude and direction. And we can draw and represent acceleration with a vector. So maybe we have an object that is accelerating in the negative x direction. Now, it's important to point out that negative acceleration is not the same thing as deceleration. A lot of people make this equivalence between negative acceleration and deceleration, but they are not the same thing. It's possible for an object to have negative acceleration, or in other words, be accelerating, for instance, in the negative x direction, but actually be increasing its speed. So let's give an example. Let's say we keep this acceleration vector. We're accelerating in the negative x direction, but that acceleration applies to an object with negative velocity, a velocity directed in the negative x direction. So we were already traveling in the negative direction. If we're accelerating in the negative direction, that means we're going to be speeding up in the negative direction. So we see when the acceleration vector is in the same direction or has a component in the same direction as the velocity vector, whether the acceleration is quote-unquote negative or not, that object's going to be speeding up. On the other hand, if the acceleration vector and the velocity vectors are in opposite directions, so here we have an object that's traveling in the positive x direction, but accelerating in the negative x direction. Now we would see a decrease in speed. But again, negative acceleration and deceleration are not the same thing. If you have a situation where negative acceleration does cause an object to slow down, it just means that the acceleration vector is pointing in the opposite direction of the velocity vector. So we have to be careful with our vector addition when we're thinking about acceleration. Another important point about the vector nature of acceleration is that if you have an object that is changing direction, it will be accelerating. So if we have an object that moves in a circular or curved path, that object is in fact accelerating, even if it's maintaining constant speed, and the acceleration vector is going to be directed toward the center of curvature of that moving object. We call this a centripetal acceleration. So anytime an object changes direction, it is in fact accelerating. And this is consistent with what we talked about earlier with velocity, that in order for velocity to be constant, it has to have both constant speed and unchanging direction. So let's do a real quick acceleration calculation here just to demonstrate what this might look like. So let's say that we have an object that is at rest, so it starts at 0 meters per second, and it accelerates to a speed of 20 meters per second in a time period of, let's say 15 seconds. Okay? So now if we want to do our acceleration calculation here, A equals delta V over delta T. Our change in velocity, we're going from 0 to 20. Now you always want to put final velocity first. So where we end up minus where we started. So VF minus VI over T. So I have a final velocity. I end up at 20 meters per second. I started at 0. And this occurs over a time interval of 15 seconds. So what we see then is we're going to end up with 20 meters per second divided by 15 seconds. And the units are going to combine in such a way to give us meters per second squared. We've got meters per second divided by seconds, so that's the same thing as, let's rewrite this here. That's the same thing as meters per second times 1 over seconds. So that's where the meters per second squared comes from. We take 20 divided by 15. That's going to get us about 1.33 meters per second squared. And that's a very simple acceleration calculation.